Today's first talk will be given by Professor Franco Maloberti from Pavia University in Italy. Welcome, Professor Maloberti. It's a pleasure to receive you here in the CASSW'22 workshop 2022 edition. The presentation is being happening in person for the attendees at Porto Alegre and also live broadcasted on YouTube. Before the start, I will introduce Professor Maloberti's CV. Professor Maloberti received the laureate degree in physics, summa cum laude, from the University of Parma in Italy in '68, and doctorate honoris causa degree in electronics from INAOE, Mexico in '96. He was a microelectronics professor at the University of Pavia, Italy, the Texas Instruments Jack Kilby Analog Engineering Chair Professor at Texas A&M University, and the Distinguished Microelectronics Chair Professor at the University of Texas at Dallas. Currently, Professor Maloberti is an emeritus professor at the University of Pavia in Italy. He has more than 600 IEEE publications, 10 books, and holds some 40 patents. He is the IEEE Division 1 Director, and he was President of the IEEE CASSW Society and IEEE Sensor Council. He also served the IEEE in numerous responsibility positions. He received the IEEE CASSW Society Meritorious Service Award in the '99, the 2000 CASSW Society Golden Jubilee Medal, and the IEEE Millennium Medal. He received the '96 I2E Fleming Premium and has received also several Best Paper Awards in his career. He also received the IEEE CASSW Society 2013 Mack van Valkenburg Award, and he is a IEEE Life Fellow. So, Professor Maloberti, it's a pleasure to receive you here to give us this talk. Please feel free to start, and the floor is yours.
Okay, thank you very much for the nice presentation. I just say my talk today is on a single inductor, multiple output DC-DC converter for integrated system. The agenda of my presentation is the following. I will start mentioning the integrated system, and after I will focus on the power management. And the activity in the power management is involving the use of LDO and also DC-DC converter. And in this category, we have two different kinds of converter. Some are using inductor and some are using capacitor. I will focus my presentation on the inductive converter. And after describing very quickly, the feature of the main inductive converter, I will move to the topic, the key topic of this presentation, that is to have many output from a DC-DC converter. In particular, I will mention the so-called single inductor double output, SIDO, single inductor multiple output, SIMO, and single inductor bipolar output, SIBO. Okay, this is the agenda, and let's move, just to remember what is an integrated system. An integrated system is something that is in a very small volume. And we have, this is implementing all the function of an electronic system. And we can have many possibilities to have a single inductor, system on chip, the first possibility. That means that you have all the function integrated on the same die. We can have a system on package, as we have here, where we have, for example, ASIC, it may be other analog section or digital section, passive component, eventually sensor. Another thing is to have hybrid solution, where we have maybe division of the analog and the sensor section and the digital sensor section connected together. using bus interfaces, and all these are connected to transmission line. The possibility to have a sensor will be expanded by using 3D arrangement, and at the moment there is some work on this area, especially for memory, where you have a stack of chip one on top of the other. But in the near future also we have a stack of chip with not only the memory function, but we'll have maybe analog function and digital function. And these chips are connected using through silicon via and metal bonding bumps that are connecting this chip one to the other. Okay. One of the important part of the system is how we handle the power. And this area developed in the last few years at a very high level, because the power is very important, and we have at the moment a lot of attention on this issue, and we call this area power management. And power management is what is necessary, to recharge the battery. And here, of course, it's important to have a very long life of the battery. It's important to have a suitable recharging time. And in the case of the so-called autonomous system, where we have no possibility to recharge, to provide the energy to the system directly with the conventional method, but the system must be able to harvest the power from the environment. Here, the power management is very important, because the power that you harvest is very low, and it's important to have ultra low power management. Another important point for system is the size and the weight. So we have to obtain the function required by the power need using a very small size, a very small weight. And this is especially important for the so-called wearable electronics that will be more and more used in the near future. For example, here we have a person that is wearing electronics, and we'll have here the so-called body area network that is connecting all the devices. And the devices can be very small things like this one that eventually is implanted in the heart to control the function of the heart itself. Okay, what is power management? Power management is the technique that we have to use to generate, starting from a source of energy that is not very, very precise and well controlled, into the supply that we need in the electronics. And here we have two different lines of action. One is the so-called linear voltage regulator, and the linear voltage regulator is normally used to generate reference voltages that are used in analog circuit, or to use the LDO, that is LDO means low drop output voltage regulator. That means that you have the input voltage is something, and you want to generate a voltage that is lower than the input, but more with a better quality. And in this region here, we have the need to have a very low noise, and also possibly to have a small size of the volume of the circuit. the main inconvenience that we have on this side here, the LDO, is that the drop voltage that we have from input to the output is also responsible of the power loss. And only if the drop is small, we have an acceptable power loss. But if the drop is large, that is not good. So in this case, it is much better to use a switching regulator. And the switching regulator are used elements that are not consuming power. So let's say that in the LDO, the drop between input and output is generated by an equivalent resistance. In this case, we have the conversion of the voltage at the input using the inductor or capacitor that are elements that conceptually are not consuming power. So here we have two different possibilities. One to have a voltage regulator based on the inductor and voltage regulator based on the capacitor. Actually, my presentation is flowing this part here. And at the output of this inductor based, we have two possibilities. One, to have high current at the output. And in this case, we need to use a very big controlling element, a very big transistor. So in this case, the transistor cannot be integrated on the chip. So we'll have on electronics, we have only the controller, and we have discrete power transistor, the output. And the second line here is that we have the regulator where the transistors are relatively small, even if the W is large with respect to the normal width used in circuit. But we can afford to have, this transistor in the chip. And in this case, we have all the voltage regulator in the circuit. On this table, you see that, depending on the choice, we have different features. One is the efficiency. As I already mentioned, the efficiency depends on the linear regulator, depends on the drop voltage from input to the output. So it can be 20% if the drop is relatively low, but that can become very much larger if the drop voltage is high. For the inductive, we can have a very high efficiency, 90–95%. For the inductorless, so using a switched capacitor, the efficiency is less. It may be that in some situation we can have more than this number, but typically the inductive based are much better than the capacitive based. Another feature here is the PCB area and cost. You see that the linear, very small area, largest area is for the inductive and medium for the capacitive based. And the cost here is the number of external elements that we have to use. And here you see that we have capacitor. In the case here, we have capacitor, inductor, and here we have capacitor. So the difference between these two cases is that externally, we have the inductor. And let's say normally the inductor is not an element that is as good as a capacitor. The quality of the generated voltage is measured mainly considering the ripple. And you see here that we have a very low ripple for the linear case, and we have a much higher ripple for the other two cases. Okay, let's see now what happens when we have a system on chip or system in package. We have a complete system. In a complete system, you have the interconnection of many functions. And, typically, you can have that some functions must be able to satisfy to high demand. Other part of the circuit are required to satisfy low demand, and other part are just in the sleep condition. Because of this, the supply voltage that you need for these blocks can be different from the one for this block and different from the one of this block. So in the same chip or on the same package, you have to provide different voltages to have the optimal use of energy. So what can be the solution? The solution is that we have a source of energy coming from the outside. Inside here, we have a DC-DC converter that is transforming the voltage we have on this point. The voltage on this point into a voltage that is close, to the voltages that you require on the different loads. And after that, you can have separate LDO that are determining the drop between the voltage here and the voltage here. But, this solution is not very effective. So one alternative way to resolve the problem is to use to group, the load into the ones that are requiring supply voltage that are close one to the other. And after to use a DC-DC converter is generating a voltage on this point that is able to satisfy the request of this group. For example, here we have around 1.8 volt, and here we generate 2 volts, and after we LDO, we go down to 1.8, 2 volt to 1.8, 1.7, 1.5, and so forth. And here we have another group that is requiring voltages around 1 volt. So you generate here 1.2, and after you go from 1.2 to 1.9, 0.8, and so forth. So in this way, we have a much better efficiency, in the management of the power. I mentioned before, the LDO. The LDO is a block that is regulating the input voltage and is able to generate an output voltage that is lower than the input, but with a better quality. So here you can have a ripple, and here the ripple is much lower. You can have a variation along time, the voltage can go up and down, and here the voltage is stable. How do we obtain this result? This circuit is a typical architecture of an LDO. An LDO, you see here, that is using the feedback loop to control, the element that is determining the drop between input and output, that is an MOS transistor. And you see that here we have that the output voltage is eventually attenuated by a given factor. And after the result is compared with the reference voltage that is stable and constant. And the difference between these two is an error. The amplification of the error is controlling in feedback loop the active device. Here we can have 2 possible solutions. One is to use an N-channel and to use a P-channel transistor like here. And of course, we have to invert the sign of the amplifier that we have here. But there is a difference between these 2 solutions. In this case, you'll have that this circuit is not only determining the attenuation of the input signal, but also is determining a gain. So we'll have that the loop gain here is given by the gain of this block plus the gain of this amplifier. And you can have maybe a stability problem, or you can have difficulty in obtaining a stable condition for this case respect to this one. But for this one, the voltage that you have in the driving of this transistor must be 1 threshold plus an overdrive above the output. So that means that since the voltage on this point cannot be bigger than the input voltage, you can have that the drop between this point and this point must be at least 1 threshold of transistor. Or you can have maybe a separate supply here, and you can have a boost. So the complication is not simple. Okay. For some special cases, especially for low power and low voltage, it is possible to obtain the function of an LDO using the so-called digital LDO. The digital LDO is replacing, the analog control of the regulating transistor with a digital control. What you do is to split this transistor in many small parts, and after we drive the gate of this transistor with a digital signal. So the signal like here is the input voltage of 0. So in a way that, the control of this transistor is at the maximum level. So we'll have that this transistor will be able to drive a current that is going into the load. So what you do is to control the number of elementary transistors that are switched on in a way that the current that is flowing in the load is such that this current multiplied by the resistance of the load is the voltage that we need. And this control here is determined by the feedback loop that is similar to the one that you have here. But here we have a comparator that is comparing the reference voltage to the output voltage. And the digital output that you have here is changing the number of transistors switched on that you have on this part of the circuit. So the voltage that we generate on this point can change in steps. For example, if you have 256 unity element, we'll have that, you switch on a number of this transistor here until we reach the required level, and eventually we can have a ringing around here, and after that, after a given period of time, we keep the target. Okay. In addition to the LDO, we have seen that we need to use inductor-based DC-DC converter. And there are many possible architecture. And actually, at the moment, there is also a lot of activity in DC-DC converter are mixing the inductor-based with the capacitor-based converter. So we have complicated architecture. But if you stay on the pure DC-DC converter with inductor, we can identify three basic structures. The first one is called a buck converter, and the buck converter is able to generate an output voltage that is smaller than the input. And you see that this kind of structure is based on the use of a switch that is switching this node between the input, between the input and ground. So you'll have that the switching here is switching with a given duty cycle, and the result is that the output voltage is linearly proportional to the duty cycle. So you see that if the duty cycle is 50%, we'll have that the output voltage is 0.5, 50% is here, is 0.5 the input voltage. If the duty cycle is 80%, the output is 0.8 the input voltage. The second structure is called boost converter, because it is able, to generate a voltage that is bigger than the voltage that you apply at the input. And you see here that, again, we have a switch that is switching between these 2 points with a given duty cycle, and the output voltage is related to the input using this parameter here. So the voltage is that you have the output is 1 divided 1 minus the duty cycle. So you see that when the duty cycle is, for example, is 0.5, we have the output voltage is 2 times the input. So in this case, we have that the output voltage is bigger than the voltage that we have in the generator here. We have a similar configuration. Again, here we have a switch between these two nodes. But in this case, the result is that the output voltage is negative. So we have an inverting converter. And depending on the duty cycle, you can have a buck function, so the output is smaller than the input, or a boost function, so the output is bigger than the input. Okay, so let's look in more detail, what is the idea of having this kind of converter. So let's say, the buck converter, you see that you have that the battery, the source, is connected to this node during the phase 1 and to ground during the phase 2. So the voltage on this point will be a square wave like this one. So for D time, the period of the switching, the voltage on this point is the voltage of the input battery. And for the time when this is connected here, that is 0. So you see that, the average of this waveform is a constant level, and it is lower than the voltage of the input. But of course, this waveform is not good. So what you need to do is to find a way to transform this waveform into the constant average. And this is done using the filter. So what you can do is to have a filter that is very good in low-pass function that is rejecting all the high-frequency components, generating this constant level. And a very effective filter that is not consuming power is made by an LC, like this one. So you have LC is not consuming power. So if you put an RC, you consume power, but if you put an inductor, you don't consume power. And the voltage that you obtain on this point is clean enough for our application. Another way, to see the operation of this circuit is that, during one phase, you have this circuit here. And during this phase, you will have that the voltage across the inductor is with a given sign that depends on the difference between the voltage on this point and this point. And the current that is flowing into the inductor is putting energy in the inductor. So we'll have that during this period, we charge the inductor with energy. During the other phase, you see that the configuration is this one. So the energy that we have on this inductor now is transferred to the capacitor. So during this phase, we put energy in the inductor and also we send current on these two elements. But during the other phase, we use the energy that we have in the inductor to provide the current on the load. The same is for the boost converter. For the boost converter, we have something like this. So again, during the phase 1, you see that you have this circuit. You put energy on this inductor, and during the phase 2, you transfer the energy to the load. But the terminal of the inductor on this part is the input voltage. So the voltage that you have on this point will go up with respect to the voltage on this point. Okay, this is the basic operation. We have more or less the same concept, for the buck boost converter. During one phase, we put energy in the inductor. During the second phase, we transfer the energy on this load. The only difference with respect to the boost converter is that, we have the inductor connected to ground. So during one phase, we put the energy on this side on the inductor, and during the other phase, we draw the energy on the other side of the inductor. Okay. Let's go back again, to the strategy that we discussed a few minutes ago about the use of many DC-DC converter to have an optimal use of energy, because we group the load, and after you generate different voltages that are able to drive the load through effective LDO. Instead of using, multiple DC-DC converter that require multiple inductor, it is possible to use a single inductor that is able to generate more output voltages. So this is describing the transition between many DC-DC converter on the same chip to a single inductor multiple output converter that is using only one inductor that is external to the chip. So what is the strategy that is leading to this solution? The idea is very simple. The idea is to have a time sharing of the current in the inductor. So we have that in the inductor we have a given current during the charging and the discharging phase. What you can do is during the effective period to send the current sequentially in the first load, second load, and if you have more than that, you have fourth, second, third, and so forth. So we have a time sharing of the current. Of course, when you do this operation, it's important to have acceptable efficiency or very good efficiency. And also, we have an important issue that is about the control. Like for the LDO, in order to have the voltage on the load, on the output, that is what you need. It's important, it is required to have a feedback loop. And the feedback loop for the DC-DC converter is controlling the timing of the switching that you have in the DC-DC converter. So, for example, for the buck converter, we have that a given duty cycle, and the duty cycle duration is determined by a feedback loop. But if you have maybe two outputs, you have the need also to determine when you switch from one load to the other load. So for two output, you need to have a feedback loop, two feedback loops that are determining these two times. If you have n outputs, you need the time, the time that is determining the duty cycle plus n-1 time for the sharing. So you see that if you have two outputs, you need to determine two times in feedback. If you have n output, you have to determine n times in feedback. And all this operation must be able to ensure stability. So let's see, what is the basic concept, for the time sharing of the output current. So the buck converter is made by the battery input. We have two switches that are determining the duty cycle. And after that, in the output, you will have, depending on the load, the distribution of energy is two switches that are closed and open. So during a fraction of the period, we have the current is going on this load. During another part of the period is going here, here, and so forth. So you see here that if you have a buck converter, in addition to the switch that you have on the battery side, also we have extra switches on the load side. If you have a boost converter, the situation is more favorable because the buck converter is made by a switch that is charging the inductor during one period. And after that, we have the inductor that is sending the power to the load. In this case, what you have to do is just to duplicate, the switch that was used to send the current to the load by N in a way that you can charge load 1, load 2, and all that. For another possibility that we have is to combine the two functions, to have a circuit that is able to generate a voltage that is lower or bigger than the input voltage. And this is an important feature. For example, when the battery is discharged or the battery is charged, so the voltage on the battery can be variable depending on the level of charge. So it may happen that when the voltage of the battery is high because we have maximum charge, you need to generate a voltage that is lower than that level. When the battery is discharged, you need to boost the voltage. So in this case, you will have in your system a buck boost converter able to perform these two functions. And this can be done by duplicating, the feature that you have on this circuit and this one. So we have these two switches that are obtaining the buck converter, and this switch with the other one that are obtaining the buck boost converter. Okay, let's see now what happened, to the current in the inductor. Probably from the basic course of electricity that there is a relationship between the voltage across the inductor and the derivative of the current. So the voltage is given by the L multiplied by the derivative of the current. So if the voltage across the inductor is positive, you will have a derivative of the current that is positive, so the current will go up linearly. If the voltage across the inductor is negative, the voltage will go down linearly. So if you have, for example, a buck or boost converter with two outputs, so we'll have that the current in the inductor will go up linearly until the switching between the battery and ground. So at this point, the voltage will start going down with a given slope. But when you change, from one load to the other, the voltage is different, and we'll have that the slope of the current will change. So in the steady state condition, this waveform will be repeated continuously. Another possibility is that we have the switching between one load and the other is during the charging phase. So we'll have that current is going up with a given slope, and after, when you move from this load to this one, we'll have that the current is changing the slope, and at a given moment, you switch, from this point to this point, and the slope will become negative and will go down like this. And again, you will have that in the steady state, you will have a repetition of the waveform. Okay. Let's see now, what I have done in this area. Actually, I've been working on this area many years ago. I started this around the year 2000. At that time, I was a professor in Dallas. And in Dallas, in the university, I had a PhD student that were also employed at Texas Instruments. And one of my students, this Hoon, was working in the power group. And he came to me saying, okay, my manager told me about a problem that we should resolve, and that is related to the control of LED, white LED, that are used in a cell phone. And at that time, the cell phone had the display plus the keyboard. And the request was to have a separate control of the LED that were used to illuminate the display and the keyboard. Well, when you consider white LED, you have that the illumination depends on the current and not on the voltage that you apply across the LED. And if you want to have a constant illumination, you need to use multiple LED. And the idea was to use many LED in series with a given control like this one that is measuring the current in this way, and after use a DC-DC converter that is making the voltage that you have on this dropping element equal to what you obtain. And in this case, you will have that the illumination is uniform. But the voltage that you generate here is 3 times the on voltage of the LED. And that voltage can be maybe 1-2 volts. So you multiply these two, you have a relatively large voltage here. The solution to putting LED in parallel is not good. So this is another possibility, because here we have voltages, and the current that you have here can be different because of the mismatch between the different elements. Okay, so the solution was to have 2 of this output, and the idea that we developed was to have, was to have a boost converter using a single inductor and 2 outputs. So the basic idea is to have maybe the inductor that is charged during the phase 1, and during the phase 2 we divide in 2 parts. We have during a fraction we charge the load B, and during the other fraction we charge the load A. For this kind of converter, the energy that we put in the inductor is able to satisfy the need of the 2 outputs. So at a given moment, the current in the inductor is going to 0. And this is a so-called discontinuous mode. So the current that you have is not all the time bigger than 0, but the current is going to 0. Well, in order to design this circuit, we had 2 possibilities. To have a ping-pong solution. So during one phase, we have that we charge the inductor, and after we discharge the inductor into the load 1, during the next phase, we charge the inductor and we discharge on the load 2, and eventually after that the current remains 0. And after repeat, so we have charge, load 1, charge, load 2, charge, load 1, and so forth. The other option was to charge the inductor, and after to deliver the current to the load 1, then load 2, and after you have 0. And you see here that we have a better possibility, to have a range of control of the illumination. So our choice was to use this method, because with this method it's possible to have a bigger range of operation of the circuit. Okay, so the second issue that I mentioned before is how we can determine these two periods. So here, if you have this waveform of current, you have to determine this time here when you switch, when you finish to charge the inductor, and this time here is when you go from the load 1, load A to the load B. For this kind of circuit, what we have done is to use a very, very simple approach. The idea was to say, okay, let's control the voltage on the one of the load, and when the output reaches the level that we need, we switch to the other. So to have some sort of master-slave control. So we have that the master is satisfied, and when the master is happy, we move to the other switch. And eventually, we control, the error that you have in order to move the time at which we stop the sending of energy in the inductor. So what you do, we satisfy the load A and after load B, but if the error is becoming too big, we increase the energy that we put on the inductor. And this is done with this circuit here. You see that here we have the two LED. Here we measure the current, and we generate, the error comparing, this voltage we generate here with the two setting. After that, we have the two error amplified, and depending on the value of these two error, we decide to increase or not the time during which we stop the charging of the inductor. So one of the issue that we had also to resolve is how to drive the switches that we have on this side, because the voltage that we have on this point is relatively high. So we had to find the way to control the switching on and off for this PMOS transistor that we have here. And this is done with this circuit. Another problem that we have is that we have to avoid that the voltage of one of the two output is affecting the voltage of the other during the operation. So if the voltage here is bigger than the voltage here, you have the risk that the switch is reversed, and we have the current is flowing in the other direction. And this is done by putting these diodes on these 2 points. After that, I returned back to Italy, and I left Texas. And also I left the good stack, but I know that in Argentina and Brazil we have good stuff anyway. Anyway, so I had cooperation with Austrian Microsystem, and with them we resolved the problem of single inductor double output buck converter. So the architecture of this one is to have two switches at the input, and also we have the switches that are sending the load on one side, on the other side. In this case, the control that we have was to have one of the load is determining the control of the switching between a battery and ground, and the other one is controlling the switching between one load and the other. So we had the control of the two time using the two outputs. If one output is affected by an error, we increase the amount of energy that we send on the inductor. If we have an error in the second, we move the switching time between one load and the other. On this circuit also we had other additional problem. One was what kind of switch we have to use in the position where we move from one load to the other. And we had the possibility to have NP transistor here, or to use a single transistor. And in this case, you know, the problem is to find the biasing of the substrate of the transistor. And the idea was to use a transistor into a well, and to use the biasing of the well with the voltage that is on the source side, on the drain side, depending on the value of these voltages. And this was done as described here. You have the bulk biasing. No, sorry, the bulk, not the well. Sorry, I'm sorry. The bulk biasing was the voltage on one side, on the other side, depending on the value that we have on the output 1 on the output 2. Okay, so here we have some detail. At that time, we have used the 0.35 CMOS technology, and the area of the chip is relatively large. So you see here that we have the power transistor located here, and this is the multiple bonding, you know, for the outputs. Okay, after that, I had cooperation with National Semiconductor, that now is not existing anymore, is part of Texas Instrument. And with them, we faced the problem to generate 4 outputs with a single inductor. So the simple control that we have used for the 2 inductors is not suitable when you have more than 2 inductors, because the control is not very accurate and the stability is not ensured. So the problem that we have can be mathematically described in this way. Suppose that you have errors in the outputs, epsilon 1, epsilon 2, epsilon n, and the timing T1 that you want to control can be supposed to be the linear combination of all the error. The time T2, again, is the linear combination of the error and so forth. So we'll have that the n times that we want to control, so 4 in our case, is described by this relationship. So the vector of time is equal to the vector of error multiplied by a given matrix. And eventually, you know, if you want to have that the error is small, you have to multiply this by a large gain. So the time that you have will be what you desire with a relatively small vector of error. So this is the mathematical problem that we want to use. And the issue is how we have to choose this matrix. Actually, we have many possibilities. Between these many possibilities, we have a very simple one that is the one that we have used for two outputs. So one output is determining T1, and the second output is determining T2. And eventually you can have the same diagonal one. So we have one time is determined by a single error, or to have a more complicated matrix where, for example, the T1 is determined by the addition of the error, T2 is determined by the error in the channel 1 minus the error in the other channel, and so forth. So you see here that we have a matrix of more complicated combination of error than this one. And actually, if you consider this matrix, this is having some sense. So you see that if the addition of error is, if you see the coefficient 1, is bigger than 1, that means that the whole system needs more energy. So that means that you have to put more energy in the inductor. And in this case, we can say that T1 is the time that we require on the switching from, let's say, if you have a buck converter, from VDD to ground, from the battery to ground. If that is less than 0, we need less energy, so we have to reduce, the energy to put on the inductor. Let's see the second equation. If the error in the first channel is bigger than the one in the remaining 3, that means that the first channel needs more energy because his error is large. So in this case, we have to increase, the time that is providing energy to the load 1. If the error in the first one is bigger than the addition of the other, that means the first channel is satisfied and needs less energy. So we can move this one back. And the same for the other. So you see that, there is some logic behind the choice of this matrix. And also, the result that you have here is more effective than the one that you have here, because in this case, we provide more energy when the addition of the error is giving the information that the entire system needs more energy. In this case, it's only the first channel that needs more energy. So we put more energy in the first channel, but probably that is too much because the other one also are able to provide the missing energy to the first channel. Okay, so the idea was, to use this technique to control the switching. So if you look at the current that you deliver, you can see that, for example, you have the switching between the channel 1 and channel 2 is here, channel 2, channel 3 is here. During the channel 4, we have the switching between this point to this point and so forth. So this is the waveform that we have. We have published this result on the ISSCC and also on the Journal Solid-State Circuit, and eventually you can find some details on these papers. Okay, I think that we have to go faster now. Okay, here are some details on the area and technology. And normally when you present a paper, you say that my results are better than the other, and this table is showing that. Okay, let's move to another example. This is the result of cooperation that I had a few years ago with ST microelectronics. The idea there is to have many output voltages for the driver of the speaker in the radio of a car. The source of energy is coming from the battery. And what happened in the battery is that the nominal voltage is at a given level, for example, is 14.4 volts. But when you start the car, the voltage of the battery is jumping down to a very low level. So you go down from 14 volt to 4 volts. And in some situation, the voltage can go up to very high level. So this is the challenging situation that you have for the input. The requirement was to generate a voltage that is bigger than the voltage of the battery, because the request was to use N-channel transistor in the two sides here, because the area of the N-channel transistor is smaller than the equivalent of the P-channel, because we have a lower mobility. So it was required to have V battery plus maybe 6.5 volt. It was required to have 5 volts to drive part of the circuit, but also it was required to generate 1.8 volt for the digital section. And the strange request that we have there is that the voltage on for the digital must be floating. So the idea was not to have a voltage that is between 0 and 1.8, but we need a voltage that is at half of the supply floating. So in this way, we have that all the digital section was operating, floating around half of the battery. The reason of this request is that when the voltage is going down at this level, you can have that the 1.8 volt is becoming very low, and the digital part is dying, is not working properly. So the circuit that we had to design was a buck, boost, and floating voltage. So the architecture is similar to the previous one. And here, the strategy I've used was to use to charge the inductor during one phase, and after that to discharge the inductor to obtain the boost voltage and the 5 volt, 4.5 voltage here. And after, for the floating voltage, we have that instead that closing this switch or having this switch in this connection, you see that we have this extra switch for the floating condition. So we have that the floating section is insulated, and they have the inductor in parallel. So in this way, we can obtain the floating voltage on this circuit. On this circuit, we had a number of issues to face. One of these is how to control the phases. So if you have this circuit, if you open this circuit and the other one is open, the current in the inductor is not able to go anyway, and the voltage on this point is jumping up. So what you have to do is to make sure that the current in the inductor has all the times some path to go. And this was obtained with some sort of quasi-asynchronous operation, obtained by using this diode that we have here. Because otherwise we have this jump that is not good. The circuit was realized using a 110 nanometer BCD process. And you see here, some experimental results that are showing the startup, and after we have the sequence of operation of the various phases, and these are the possible voltages, and you can identify here the floating voltages following half of that. Okay, the last example that I want to show you is the last study. Oh, this is accepted, but now it's already published on the journal Solid State Circuit. I'm sorry, I didn't update the year here. Is a single inductor bipolar output. This is satisfying the request of active matrix organic light emitting diode, AMOLED. This is probably that is used in displays, and this kind of circuit are using positive and negative voltage, and the positive voltage is used to control the current, and this is for the pixel level color control, and the negative is controlling the brightness. For the request that we have is that the positive voltage must be very clean, so very low ripple, and the negative voltage is more acceptable to have some ripple there. So the solution to this is to use single inductor bipolar output. That is, for example, charging, the inductor, and after you discharge the inductor in the inverse mode, so the current is flowing in this direction to ground, and after that we discharge the inductor in the boost mode. So we have the generation of the negative voltage and the generation of the positive voltage in two different time slots. During one period you control the negative, and during the other period you control the positive. The problem is that the ripple on the positive side is normally bigger than the ripple in the negative side. It may be, you can make them equal, but that is not acceptable. So the issue is to be able to reduce the ripple on the positive. The idea that I had is the following. Instead of having a separate control of VP and VN, what you can do is to have a floating generation of VP minus VN, and after that we put an anchor on VP. So if you have that the VP minus VN is affected by an impulse, by a ripple, all the ripple is going on VN, and VP is fixed. So the idea was not to generate during two different times VN and after VP, but to generate at the same time VP minus VN. The implementation is actually, at that time I had a student in Pavia, and the student made a study. That was a master student, and they made a study at the functional level, but in Italy, it is not required to have silicon for master student. So after that study, I asked the people in Macau, where I have a cooperation, to implement the solution in the silicon. And the person that was working on this project added some feature, like the use of a flying converter, the flying capacitor, sorry, that is this one here. But you see that, we control, directly, the voltage Vp minus Vn, and we put an anchor here to fix the voltage on the P side. So we have that during the charging phase, we put energy on the inductor, and during the discharge phase, we have we send the current into the capacitive load and also in the load here. Here we have some additional issue that are related to the parasitic capacitance that resolved. But I think that the concept is hopefully clear. Okay, thank you. So you see that here, for example, we addressed the problem to have the parasitic capacitance that is discharging, the current in this way. So we had to resolve this problem and to compensate for this one. And this was done with the addition of this current generator here. But I think that all these details are maybe complicated to discuss at this level. I think that what is important to see is the experimental result. And you see that here we have that depending on the load current that you have, and the typical current is in the order of a small display in the order of 100 milliamp, you see that the efficiency can go up to about 88, 89%, depending on the voltage of the battery. So even if the battery is going down to 2.8, that is very low voltage for lithium-ion battery. Lithium-ion battery is not discharged at that level. So you see that the efficiency is very good. Another thing you can observe here that the positive voltage is very clean. So this is 10 millivolts. So the ripple that you have here is less than 1 millivolt. But for the negative side, we have more noise, and also we have these spikes here. So these are different situations. So in conclusion, with this circuit, we have been able to satisfy the request of a very small ripple, less than 1 millivolt in the positive side. Okay, so in conclusion, in the future, more and more, integrated system will require many supply voltages that are changing dynamically in a way that you customize the cell for an optimal use of the power. So depending on the activity, what you have to do is to increase or reduce the supply voltage. I have not made an example of the voltage required for the transmission. And anyway, you can understand that if you want to transmit a small signal, the voltage in the required for the power amplifier can become bigger, while when the voltage, the signal you want to transmit is big, you have to increase the supply voltage. So you need to have the possibility to change dynamically this voltage. And one possible solution will be to use the DC converter using inductor. And after that, you can refine the voltage with LDO. What we have discussed today is various implementation of single inductor double output, single inductor multiple output that are either with boost and buck converter, and also the last one is the single inductor bipolar output. Thank you very much.
Okay, Professor Maloberti, thank you very much for your presentation. Now we will start the Q&A session. We already have some questions. I will start from for the questions in the chat, okay? Then I will open for the auditorium, so they can ask live the question, okay? The first question is from Dalton Colombo from Federal University of Minas Gerais in Brazil. Thank you very much, Professor Maloberti. It was a very interesting talk. For the SIMO, is there any special attention technique we need to take care to not turn on the internal diodes? With negative and positive voltages, I might think that we need to use, for instance, isolated wells. Thanks a lot. You also can see the question in the comments, right? So this is the first question.
Okay.
Can you comment about if it's necessary to have special attention to take care in the SIMO to avoid the turn on of the internal diodes? What do you think? You can hear?
No, I don't hear. Maybe you can tell.
Hello, can you hear me now? No?
No. You can type on the chat. Type on the chat.
Okay, I'll type in the chat. So I will type in the chat the first question. Okay. Yes. We have some audio issues. In the auditorium, can you hear me?
Yeah.
Okay, I can see your hands.
Yeah, I see that.
Can you see the question?
Okay, the issue of the well, right? That is a technological problem, right? I think, of course, isolated well is a solution. Yes. Yeah. So it depends on the technology that you use, of course. Actually, one of the problems that we had was the high voltage that you have in some part of the circuit, and the use of the flying capacitor was attenuating that voltage. But of course, the switches that are switching to the negative voltage must be able, to have suitable substrate. Yes.
Okay. Yeah. Just a second. Can you hear us now, Professor Maloberti?
Okay. Yeah.
Yes, so we have a second question from Professor Alessandro Girardi from Federal University of Pampa. First, thank you for your nice presentation. Can you comment on the DC converters for energy harvesting IoT applications, in which the available energy highly varies in time? Are inductor-based converters suitable for ultra-low output voltages?
So it depends on how fast it's variable. Yeah, it depends. If you have energy coming from a solar cell, for example, the energy is not changing so quickly, so you can use that. So everything depends on the clock frequency. typically you have 1 mega or 2 mega of switching frequency. So I think that tracking the variation that you have at the input is not an issue.
Okay, so
I don't think that the change in time of the energy of the one that you harvest is very fast. I
okay,
don't know if you have example of because if you have 2 mega, it may be the reaction of the feedback can be maybe millisecond or even less, microsecond. 10 or
okay,
20 microsecond, I think is not an issue.
okay, perfect. So now I will open for the questions in the auditorium. Leonardo, are you there? Is there any question from the auditorium?
Yeah, we are here. So, do you have any question?
I can see. No questions from the auditorium for now. Meanwhile, people can write the questions in the YouTube chat. I have some questions from my own here. The first question is there a limit of output power so we can use the SIMO or SIMO converters? Let's say if I need to provide 10 watts for a load, can I use SIMO or SIMO topologies? Because most of the examples are for very low output currents in the milliampere range. Can you comment about that a little bit?
Yeah, when you have a multiple output, we have a problem of the quick change of the current is more or less the same problem that we have a single inductor, single output. So we have to react quickly. But the problem you have a crosstalk between one channel and the other. And one of the feature that is considered, the minimum crosstalk. 2 days ago, I had a meeting with people in Macau, and they also are working on multiple output series converter using capacitor. And they claim that the crosstalk for the capacitor-based multiple output is better than the one with the inductor-based. Yeah, but the architecture they have used are with also inductor on the chip, so that hybrid solution. So it may be that instead of using the inductor only, the pure inductor architecture, if also use capacitor, will be better, but we are going in the direction of more complicated structure.
Okay. And about when we use single inductor multiple output, for example, we rely on the inductor, one inductor only. Is there, let's say, any specification for the inductor about the quality factor, for example, or which kind of inductor, what should we take care of about the inductor design?
Yeah, actually, if I remember, we used the Murata inductors at that time. I don't think there is a specific request, for the inductor when you have a multiple output. I think it's the same for the normal. Of course, you need to have a low resistance from the inductor. And also, here you have that the current that you have in the inductor is much higher than the current that you have in a single one, because we have only a small fraction of the current that is going in a single load. And the current in the inductor is the one that is the one required to satisfy the need of power of all the load. Of course, if you have two separate DC-DC converter, the power in the single inductor is much less, or the current is much less.
Yes, and maybe the total volume of the prototype should be smaller with a single inductor, right? I have another question about the switching frequency. When we have single separated single inductor, single output converters, we have, let's say, 1 megahertz switching frequency, 2 megahertz. When you go for a single inductor multiple outputs, is the switching frequency much higher to provide the control, and if that frequency can impact on switching noise in the whole circuit? Is there an issue about that, or we can use single inductor, single output, multiple output converters with no problems?
The switching frequency is almost the same. The chip that we have used is 1-2 mega. Of course, the power that we consume is more. I don't know if no, I think almost the same. Yeah,
Almost the same.
I don't think it's. Let me think, because we have not discussed about that issue, but I think it's not a problem. It's not required to increase the frequency. No.
Oh, okay. So that's good. And I also have another curiosity. Let's say in slide 27, you showed a SIMO converter, I believe, and you generated a floating output voltage, I believe, for the digital part, 1.8 volts. Do you have to put extra protection to generate these voltages or not? Because they will be floating to supply a digital load, for example.
No, the floating voltage was around the battery divided by 2.
Okay, so there's no problem. It's
no, because the issue is that if you lock the negative terminal to ground, when the voltage of the battery is going down, 1.8 is becoming much smaller. So the idea was to have the 1.8 is following the reduction of the voltage of the battery. So
okay, perfect.
That was all the digital section was floating.
Okay.
That's
so okay. Let's chance. Any question from the auditorium? No.
Sorry.
Any question from the auditorium here? I
No.
cannot see. No.
No.
Hand raised. Okay. So our time is finishing. So now I would like to thank Professor Maloberti for this nice presentation. Thank you very much for accepting our invitation, and I hope to see you maybe next year in Brazil in person. Right? You could not be able to go in person this time, so maybe next year. Okay.
Yeah, hopefully yes.
Yeah.
Now we are starting flying again.
Yeah, for sure. Here in Brazil, also we are starting to travel more safely now, right?
Yeah.
So I hope next year most of us would like to go to in-person events right now.
Yeah, hopefully yes.
Yes. Okay. So thank you very much, Professor Maloberti. And now I declare this session closed. A good event for everyone. Okay. Bye-bye.
Okay. Thank you. Bye-bye.